Welcome to the Rust Meetup Karlsruhe. And I'm going to present a package that I've been working for quite a while. So it's called Mannequin, which was the only name I could think of. I had Pinocchio in mind, but that was already taken. So yeah, it was the closest thing because it is a crate or package that allows you to do some sort of robotic algorithms related to kinematics. And it's a framework that allows you to build libraries that you could use in a game engine or and so on. Yeah, I'll go to that in a second. I skipped these one because we're just for Wi-Fi and so on. So in ascending order, it will get from boring topics to the cool stuff at the end. So first I will talk about myself a bit and my motivation, why I do that. There will be a small primer into robotics. So don't know, has anybody listened to robotics on the way? Yeah, please too, perfect. So there's a bit of robotics in there, and yeah, then I will go to the actual package, talking a bit about the structure and interfaces that I designed for that, because the package was intended to learn Rust. So I'm rather new in Rust still. And last, I will show how to use it in Godot and VR. And after the second talk, and if there's time, I've got my Quest 3 there. We can try it out if you like. Yeah. So there's a live demo planned, not part of the talk directly, but yeah, you can see. So a little bit about myself. I've been to the Gulasch Programmiernacht 2 weeks ago, and while strolling around, there was one exhibit on the top floor, and that gentleman there is Armor 3. And I did actually my PhD thesis in the lab while we were working on that one. So I didn't build it, but I helped it to get a bit smarter. So my PhD thesis was about learning these functions that we are using, or that I'm using in that package. Yeah. So it was a bit machine learning oriented, but not directly. So yes, so that means primarily I work as a data scientist. By trade, I'm a roboticist and cognitive computation scientist, you could say. Machine learning also a bit. I worked at KIT in my academic career, and also at FZI. So, and I am a Rust enthusiast, as you have might guessed. So the reason why writing this package, yeah. So what was the idea for that? And we have to go a bit back into time for that, roughly 10 years. Where I was being tasked because I was learning kinematics. So I teach a robot that he knows when he moves his arm, how his arm will move, because he can only control his joints. But what happens in the real world, that is something we have to learn. I mean, people with kids know that babies are grasping all the time until they don't knock stuff over, or at least do that intentionally. And learning is great, but you get never accepted to any robotics conference without experience and ground truth. And we had a motion capture system in our lab. So my boss said, put these tiny bubbles on the robot, track it, and use that as a ground truth data. But that's manual labor, like a lot. That would have taken me at least 3 hours to label that. Instead, I created a software that did it, and I only needed 3 weeks for it. It was fully automatic, but it was nice. And we were even talking about maybe founding a startup with that one day. I don't know. And it actually worked. It was written in Python. And I can't find my mouse. Can I? I can't start it. But you've seen it. So it was really, it is a model-based approach. That means you have like a mannequin or an avatar, and you fitted that into the data. And usually if you have motion capture, it only finds rigid bodies on your so configurations that geometrical that don't change. Even if you put them on elastic skin, that means you have to use this actually all the time, the tracking, and you have to do a lot of manual labor. Probably that has changed in the last 10 years, but I didn't look into that. Yeah, and I started Rust. So I was also in desperate search of a problem. So I had a solution, and I was in search of a problem. Yeah. So I looked for something that I could keep me occupied, that I could use to learn Rust. And while doing that, I stumbled upon the Biomechanics Foundation, which is a group of PhD students from California who decided that all biomechanical software that is open source is not really good, and I wanted to create something in Rust. And I said, hey, let's join forces. I will do the kinematics part, and I can use some of theirs. Well, it's open source, of course, but I consume it and give something back. So a bit of a primer first, robotics. And yeah, the handbooks of robotics. Who is interested, read that book. It's only 2,000 pages. I don't know, it's easy read. Yeah, no problem. But I want to talk about 4 functions. So the first one is the kinematics. So kinematics, I mentioned that, is if you know your joint angles, where is my arm in space? You could say that. That's the forward kinematics. So it's a mapping from the joint angle space, which usually is called configuration space, into this task space, which is the Cartesian space. Or it could be 6D for if you include orientations. Inverse is the more interesting point, and that is what the package right now tackles. That is going backwards. So if I know there's the beer and I want to take a sip out of that, how do I do that, right? For a robot, that's not trivial. So it has to know what is my target, and it needs to know it in a language that it understands, which is joint angles. Yeah, you can only put control on the motors to get to a certain position which you can read. And yeah, but where you're in space, yeah, that's what I learned actually in my PhD thesis. We also have dynamics. I won't go deep into that because I want to include it, but it's not. And that's very related, but it's translating momentums and forces into accelerations of your robot. You would need that if you play computer games and you hit your opponent and your opponent just collapses into the ground. That is basically inverse dynamics, what is called, because you put a small torque on the force on the joints so that they collapse and let gravity do the job. And having that realistically simulated, that's the inverse dynamic. And that is also relevant for biomechanics. So it's not only useful for gaming, but they are obviously closely related. So a bit of formulas. If we have that mapping, the forward mapping from joint space into task space, that's always easy. You can model that. That's just geometry and easy to do. Going backwards, inverse is not trivial because usually it's an ill-posed problem. So if your robot or you can reach a target in an infinite amount of solutions, right? It's redundant, yeah. So you can't simply invert it because which solution to take? Because there's infinitely many. So that is difficult. And what you usually do is you do differential kinematics. So you do a gradient descent. And for that, basically you need the Jacobian matrix. Probably you have that in linear algebra at one point. That is simply a matrix that has in its columns all partial derivatives. So if you think about it, you take your arm and wiggle each joint a little bit. The vectors that arise from that is in the columns. So you could see that on the image. So that is a screenshot from the software I did in that time. For many points, so usually you're in robotics, you're interested only in the hand, but for motion capture, it would be many points. And if you move only one joint, you see basically what is going to move. And it's always perpendicular, because that's how rotational joints work. And for basically computing the inverse direction, you take the forward kinematics, so you put in some joint angles, you get a position in space, easy to compute. And if you take the derivative of that, there's a missing point, I'm sorry, then you can make a local linear approximation to that function, and then you can basically go in a gradient descent towards your solution. You get something that is called the pseudo-inverse in there, which is basically what resolves your redundancy and so on. For simple cases, you would just basically do that you invert the thing and do a certain step, small step, and continue until you reach your target. So it's, in theory, pretty simple. It can actually be even a bit more simple because in the most cases, it's sufficient to just transpose the local gradients, the Jacobian matrix, and you'll get well enough solutions, at least at the beginning. And at the end, it will be starting to wriggle around the target because it can't determine its step size, but it's fairly well at the beginning. Also, what is more advanced, I'd say, you see from the formula, and don't check it, I hacked that in early before the talk, is if you have infinite many solutions, you have the liberty of picking something that satisfies another goal. So you could say, I want to reach the bottle, but I want my elbow to be as high as possible, or the norm of joint angles should be very minimal, and so on. You can do secondary optimizations. Okay, that was the theoretical part. Yes, and you can do it without the differential stuff, which is more modern, that came up in the last 10 years and is used in computer games. But you remember maybe that when Mass Effect and Andromeda came out, yeah, that they had huge problems with the kinematics. Yeah, that is related to things like that. So Jacobian, yeah, that is the interesting part, because that is at the core of each algorithm that you will have. Yeah, what you build on top of that is not so much important. This one has to be done and it has to be efficient. So as I mentioned, it's the partial derivative. So each column has a local derivative, and it's a very simple algorithm actually. Yeah, you go over all joints in your chain or in your tree. You take all the children that come afterwards, and for each of them, you just compute basically the vector to the tip, to the pivot element, and you just take the cross product with the axis, and you have the value that you need, and you put it in the correct rows of the column, then you're basically done. So it's a very straightforward, simple algorithm. It's a bit more complex if you want to do it with orientation, but even not that much. So it uses the forward kinematics in the step. And this has to be done quite often. And it is you have to pass twice through your chain. So that is something that can be slow. Yes.
So rotation isn't modeled here, right? So okay.
It's on
axis only moves around.
Yes, it's a revolute joint around one axis. Yeah. Usually, if you have like your shoulder joint with 3 or more axes or complex joints, then you'll take 1 degree of freedom at a time. Sure.
You only model like the position.
In that equation, yes. But it's pretty straightforward. If you use axis angle notation, then it's very easy to translate. It's even simpler actually, but I didn't want to include it here. Okay. If you're interested in how to code that, there's an excellent lecture, which is easy to understand. So that's where I took the picture from also. Yes, it's getting more interesting, I think, I hope. Mannequin, yeah, as I mentioned, not the best name, but at least it goes in the direction of what it does. And it's an optimized kinematics framework. It will eventually, in a few years, be blazingly fast because it's written in Rust. It maybe is. I have not run any benchmarks. So I guess it is. I'll check. And it's more an educational project, as I mentioned. First, I wanted to learn. I wanted to be able to create well-designed and concise interfaces, leverage the type system where possible. Yeah. So the type state pattern is something that we also in our group like a lot, where you basically in the type encode already constraints, for instance. And yeah, make stuff simpler and accessible. Yeah, I try to enforce it as much as I could. And I wanted to be as generic and agnostic of any linear algebra package as possible. So it should be compatible with any array, with ng-algebra, with fair, with Godot. And Godot is something that will come in this talk up. It is intentionally a bit over-engineered, I guess. Yeah. So what were 3 weeks in Python and fast enough to be real time? I think it's 2 years now or something that I'm working, but I don't invest full time, of course, into it. Yes. And in the end, I want to do motion capture and help the guys from the biomechanics group. It's definitely far from finished, but it's in a demonstrable prototype state, I would say. Trees in Rust. So if you look at the kinematics, if you have a classical industrial robot, it's just a chain. We have a few of those limbs, and we span up a tree, kind of, yeah. So having an iteration over that is the important part for the core of computing the Jacobian matrix. So what I was really working on, and working with graphs and trees in Rust is, let's say, different to what you would do in Python. I tried a lot of working with references and so on, and of course I wanted to be also mutable, which simply I did not. I had to stop at one point, and that was when the project started to sleep for half a year. until I read a good article, how you do that with arena allocation, where you basically just reserve a chunk of memory and you own it, and you do your own manual managing by just using indices on top of it. I thought at the beginning that is not very beautiful, but it's the way one does it. It's fairly safe and it works. Yeah, a bit of a trade-off, and but it is better than the alternatives. And as far as I digged in, pretty standard. It's used everywhere. Nothing new there. And I wanted it to optimize prematurely, because that's good standard, of course. And I wanted it to be as fast as possible for depth first descent in the tree, because that's what I need for my algorithm. So I wanted to have basically a tree that can be converted in an optimized tree, which is basically all the nodes sorted already. So you waste a bit of time for sorting, but then iterating of it is very fast. You just iterate over the list that is already there. And then you can also have mutation very easily, because slices give you the opportunity to iterate mutably over them. If you want to do that on your own, that is difficult, I found. Not going to too much into detail, and I should have probably not skipped that at the beginning. You can watch the slides live because I put them on GitHub, where you can find them at least later. Yeah, I would definitely should not go too much into detail, but I tried to do it as beautiful as possible. So everything that has somebody, all the trees have in common, that I put into the base, into a base iterable class. So for me, all traits have usually an capable, so something that is an adjective that describes what they can do, an ability. And this one would give you the root. It gives you your children that it has, because every tree needs that, right? A directionable tree allows you to create something that is optimized for a direction. An optimized directional tree, and this one is still not fixed. You can add stuff to it, because it still hasn't sorted its stuff, its children, so you can add new things to it easily. The optimized one, which is created from that method, gives you iteration and mutable iteration, which would not be possible on the other one. And finally, we get to a trait and struct, which has the optimized depth first iteration. A word on nodes. So you want to carry some sort of payload, right? So instead of asking the user to fulfill a trait to that, so that I can use it as a node, I have got a node that just uses any arbitrary payload you put into it. So it becomes very easy. Using the tree is near trivial. That's kind of a unit test, how it looks like. You just create the tree and you say, I want to have it carrying strings. So you don't have to implement get my siblings or whatsoever. That's all just done there. You can just add stuff to it. And at the end, you just want to convert it into an optimized string by just using it into. Yeah, so it will be casted into it. You have not to think about anything. And the good thing is, if you had a tree that were not optimized yet, and you just put it in your algorithm and you wonder why they're so slow, because it's not optimized. That's not possible, because the algorithm will expect the trait that is an optimized tree. So you can't put the wrong thing into it, so it becomes very easy to use. And a nice side effect is, if you have this architecture, and I iterated 100 times over it, but once you have it, it is very easy to, because it's so modular that you have only very, very small stuff to write. Probably now I could do that today, I guess. But yeah, I learned a lot. I could not come up with an architecture that at the beginning. Ollie helped me a lot in the run in between. So yes, in the community. But that was pretty neat in the end. Yeah, computing the Jacobian, now won't go too deep into that. I just want to point out that you don't see the indices anymore, right? It's not C-style code. It is really everything in iterators. And it's just you iterate, you iterate over your nodes. And for each node, you iterate over the tree of children that it has. And at the same time, you iterate over a data structure which holds your metrics. And that's it. And it uses only Rust means. So the matrix is written into like a float, and you just remember the columns and so on. So you can cast it or convert it into any linear algebra representation that you will have in the end. So it is completely agnostic on the back end. That was basically been the core and the core algorithm thing that would have taken a day in Python, took half a year in Rust, but I was a learner, you have to say. And it is for reusability in future in mind. The robotic structure itself is simpler, way simpler. And there is only that you have got basically a base class, which is, where is it? The Mannequin, and every algorithm, the variant of an algorithm that you want. So how do you compute the forward schematic? How do you do the inverse? Should it have some special thing? It's just plug in and play with the type system. And it delegates it. It's like a mix in Rust or in Java languages. Yes, so word on how it's handling. It is, if you want to write a new backend, let's say there's a new fancy linear algebra that you want to use, or game engine, you will only have to fulfill one single trait, which is the rigid body trait, which encapsulates a few of mathematical operations that are used in the algorithms. But in the end, it is really just 100 lines or something that you have to write, but no matter what kind of application you want. So it's a framework. It's not something ready to use. You plug it in for something. So Mannequin plus Godot would be something you could then use as an add-on in Godot, for instance. Yes, all the algorithms, like computing the Jacobian, is agnostic of what you use as a framework. Everything is hidden behind interfaces that you just call, and it's delegated in the end to the mathematical operations. And it's Rust, so that means it's zero cost. Even though it's all abstracted away and neatly and easy to read and easy to maintain, that is free, basically, yeah. Okay. The fun part, more fun part, I guess. Godot. Why Godot? We have Debbie at home, yeah? Good question. I did not want to learn Debbie too, and Godot is just easy. We have a really good community in Karlsruhe, so the Godot Stammtisch is really nice. So I met Sebastian, I met Matthias there. So yes, that is definitely an advantage. We want to write a biomechanics package that biomechanics researchers should be able to extend. And not everybody speaks Rust, not everybody speaks Godot script, but the burden is less, I'd say. For paths that are not speed optimized, that is fair also to use, right? In the core of the algorithm, we want speed, we want the safety, and that's the reason why the optimization there makes sense. Also, it's very easy to create UIs that are appealing. Godot itself is written in Godot, so looks good. And yes, and its Rust bindings are available. And there was a Black Friday deal, and I bought a Quest, and I needed a reason. And Godot runs within the Quest, if you not for Rust, of course, unfortunately, but you can develop the game in a window, and the world around you changes instantaneously when you move that in the window. That is pretty sick, actually. So it is appealing. Everything should work out of the box, and I wanted to try out whether that works. So again, not going into code, but that is how Godot script would look like. I used a Python syntax highlighter for that because there's none for Godot script, and it works pretty well. So it is inspired by Python, mildly said. And yes, if you look at the Godot interface, it's not even very much longer. It is like a one-to-one mapping, and it is very well done. That's what I want to say simply. So all the information you find for Godot script, and there's a lot of material for Godot because it is very popular for schools, projects, and so on. So you get a lot, and you can transfer it directly to Rust. So that helped me tremendously. Yes, I did a toy project. This time there's a link if you want to look at that. I put in quite some effort to get that running. The presentation is the GitHub pages to that project, by the way. And yeah, I just wanted to see whether it works. I wanted to get it into classes, and yeah, I created a small sandbox, a demo project. And I want to convert it eventually into an add-on for Godot. There's maybe a potential helper and interest in that, in the first row already. And it demonstrates the application of several algorithms of an inverse kinematics. And I guess, yeah, challenging Quest. I wanted to put it also on the Quest. The Quest is a standalone headset, or you usually use it as one. That means you don't connect it to a PC. It has its computer in it. It runs on Android, which is a challenge, I guess. But GDA extension, which is the Rust bindings to Godot, provides instructions for how to do that. And I followed them. I found out I depend a lot on matrix inversion and linear algebra. And the physicists among us know in which language those are written always. Fortran, like all, plus, and the others, Open Plus, they all written in Fortran. And I did not want to translate that on Arc, Linux, Android. So I wanted to go around that, and I didn't want linking. I don't know how to link on an Android system. Just did not want to do that. And I found FAIR, I hope I pronounce it correctly, which is a linear algebra, which is completely written in Rust, and even faster than a couple of those it had established, just because parallelization and fresher design, new algorithms, I guess, also. And I created a backend, and that was really just a matter of a few hours. I went into Discord, and they told me that I basically should learn again a bit of linear algebra. So I got a lot of help. Don't look at the code. I use stuff that's numerical, not as stable as it could be. And you sometimes see that actually, the demo, if you look closely. But yeah, nevertheless, it is. I got it running, and that was happy with that for now. And it was surprisingly easy to get that onto the Quest. So it did all that in a single day. That was possible. That was good. It was about Easter holidays, I guess. Negative, it needs Java. I had to put Java somewhere on the slide. And it installs like 20 gigabytes of stuff that I didn't need. I had to install Android Studio just to get the right version of the SDK. I tried it really by hand, but no way. I gave up, and it did the way they wanted, and I've got enough space. So quick demo. I don't know, can I do that even full screen? That makes sense. That does not work for you, I guess. It worked here. How that looks like. So I also bought a Humble Bundle deal, just some fancy science fiction environments. And that's a nice thing in Godot. You just click it together and it just works. And so that is the first. So there's 4 tables with different algorithms. This one is just what you've seen is if you just do a simple gradient descent. So you pick up an object and the robot tries to converge to it. This one would be the more sophisticated that has a matrix inversion into it and is more stable. If you had looked closely at the end, it is a bit more stable in converging to the final solution. The next one is that's still Newton. Now it does 2 things, so probably it's from labeled. This one is with secondary goal. So there the robot tries to move the elbow to the blue stick. If you later try the Quest, you will only have that one and without the fancy environment, so it's a bit easier to get into it. But yeah, you get the idea, I hope. It's easier when you try it out, and I didn't want to make the video too long, and I thought, why not? It made it good for good title slide, and it's difficult to pick up, apparently. I managed. And here I wanted to show that basically the robot is capable of crossing blades with you. I did not manage to get that because that is a real fucked up kinematics. If you have a very long leverage at the end, that thing does not converge anymore. So it just tries to tip in the middle. So I cheated a bit there. I know how to resolve it, but kept it in the video because it kind of looks cool. Yes, so that's basically the demonstration. Closing remarks, yeah. What's next? Benchmarks. Yeah? I claim that it's fast. I should prove that it's fast and compared to others. There's probably also like 5 other libraries in Rust, so I should compare to those. There's definitely one in C++. These were the guys that already had Pinocchio, so it would have been difficult to pick that name. Documentation is, tests also a bit. And I want more algorithms, especially for the biomechanics guys. The inverse dynamics is important. So there's Roy Featherstone's, that's the algorithm that everybody uses, because it's really in linear time, or in linear time, I guess. And the other way, also the because it's just a part of the library. So yeah, I want to have that like a complete library where you can just, as a toolbox, select what you need. Build an application to help biomechanics with that, and do my own motion capture idea, which was the original inspiration. Maybe I get there one day. And if there's interest from the community, why not provide a Godot plugin? Because I think inverse kinematics and dynamics is there behind what you would find in commercial game engines. That would be basically my conclude my talk. If you want to try it out, that is what you would see if you take on the quest in the corner over there. We can do that after the second talk, let's say. But apart from that, do you have any questions? Questions?
How do you test?
By going into VR. You are allowed to test it. It's okay. How do you test it? Yes, good question. You draw it's not limited to 3D. We can also do 2D. You just take a very simple toy example. Okay, it's 3D, but you only access one, like kind of 2D. And then you can basically do a simple robot with 2 joints, and you know from there to there it has to reach those joint angles. You know what your target is, and you let it converge long enough. For such simple cases, you get easily 5 to 10 or 6 digits of precision, and then you stop the test and count how many iterations you have. That is so reproducible that it does not change. There's no determinism in there. So you can test that basically not too difficult. How you test it for benchmarking? I mean, build an octopus, build an elephant. A lot of joints and let it run and see whether it really, how it scales with the number of joints. Build something crazy and build that in a different library in C++ or whatever, and check how long only that process takes. That would be the benchmark I would use for that. Ollie?
So what was the sword?
Yes.
Sword is also an extension of the whole thing, or like it only from our perspective it looks like a separate item, but it's part of the whole thing.
Yeah. So it's not learning involved at any. That would have been my PhD thesis. Yeah, my PhD thesis, I did not use swords. My professor would not have allowed that, but you know what, we had like tiny rakes or something from the playground that were easy to grasp by a robot. Sword would have been better. Yeah, no, it is kind of the moment you grab it, also in your body schema, you call that, or body image, adapts to that.
How you simulate it? It's basically another edge on top of the graph. That's
the intelligence is called Blender in that case. Yeah, so the robot is actually from Laufen, from a company called Schank, so very nearby. They unfortunately don't produce that robot anymore, but I had the models from SZI still, and they probably still have got those robots standing there. And it just looks cool. And it has a shiny reflection, so I put it in there, and the sword, I have found that somewhere. So it was quit, or I don't know. All right. Then I'd say a couple of minutes to switch to another presenter, and thank you.